Welcome to Spring LIB.
Here we're gonna discuss an oscillator. So what we have basically, or could be, is let's say a spring with a mass which is oscillating back and forth, and this spring has a spring constant K. To solve for this motion of the spring, or the mass connected to the spring, we have two equations, the Newton's equation F equals m times acceleration, which is the same as the m times the second time derivative of position, which is denoted by x dots. It's the same thing as writing dx2 d2t. But I will stick to this notion because it's a bit easier to write that. And secondly, we have the force of the spring, which is minus kx. So, and the minus here is because the force is always pushing you back, okay, towards the wall. So it's a negative force, it's not pushing you forward. And now, if we combine these two equations, we can solve, or we can get the equation of motion for this spring. So we can see that we have m x double dot equals minus kx. Okay, so this is our equation. And this can be solved by having an ansatz on a sinusoidal form. And we can just assume that x is equal to a, which is the amplitude, sine omega, which is the angular frequency, time plus offset. Okay, and doing a first time derivative on this, we will see that a times omega, because when we derive a sinusoidal, the constant falls out. Sinus becomes a cosine, omega t plus omega naught. And if we continue once again, we'll see that we'll have a omega squared, because the omega once again falls out. Now when we derive a cosine and get a sign back, we have to add a negative sign, sine omega t plus omega 0. What we see here is that x, or basically we see, for example, for this one, that this is equal to omega x, and this is equal to minus omega squared x. Oh, actually this above is not true at all because we have a cosine, but this one is equal to minus omega squared x. And we can actually see now, if we compare this equation with the result we just got here, we can actually see that we write them next to each other. We had minus kx, and here we have minus omega square x. Okay, and now we can see that k is equal to omega square k. There was a small mistake here because we have the m here, which means that we have x equals minus k over mx. Okay, so this is the one we should have compared. So it means m here, we forgot that one, and that's k over m equals omega squared, and leads to that the omega we had in our equation is equal to the square root of k over m. All right, so this is important. Now we have our sinusoidal solution oscillator, And now we can look at the problem. We're given an function, or the oscillation, which looks like this. It's actually the velocity, so it's the x dot Vx, and it's given in centimeters per second. It starts up here, goes down, and comes back up. We're given that the top in the beginning is 20. Over here, let's write this in red. Here we are at 0.4. This is time in seconds. And here we're at 0.8, 1.2. And this here is 1.6 seconds. Now, if we would plot now the sinusoidal function, the x position just right below it, it would look approximately the same, just it's a sinusoidal function. Also, we can see from this function on here, and if we compare it to our equation here, we can see that cosine of 0 is 1. And this right here, we started cosine of 0. That means that this constant omega naught is actually equal to 0. So we can skip it in the future. And if we would now plot x, which I show here, just below it, it will look something like this. We don't know the amplitude, but it should have the same period. So that means that we should look something like this, okay? And now, if we want to solve these questions that we had, first of all, we're asked A, what is the period? And the period is given from top to top. And if we read from the figure here, we can see it's 1.6 seconds. T equals 1.6 seconds. B, we're asked what is the frequency of the oscillation, and the frequency F is just 1 over the period. And if you take 1 over 1.6 seconds, you will get 0.625 hertz. And hertz is the unit for 1 over second. C, we're asked what is the angular velocity, omega. And we saw before that we could write it as the square root of k over m, but we're not going to do that. We're going to use a much simpler equation, and that's 2 pi over t. And because the angular frequency is also the time it takes to do 2 pi radians, which is one oscillation. And if we calculate this, it's 3.93 radians per second. If you continue, D, we're asked what is the amplitude A of x, because the amplitude is this A here. But we can also see that if we know that what this is here, because that's what we're given the figure, is the x dot, we see that x dot in the beginning is actually 20. That means that we have A times the angular frequency equals to 20 centimeters per second. And we can just then say that the amplitude is 20 over omega, which is 5.1 approximately 5.1 centimeters. And also we're asked, at what positions do we reach this maximum amplitude? Well, it is these points here. And this point here, I mean, the sinusoidal function is displaced 90 degrees or pi half radians from the cosine, and just calculating or just comparing the two figures, we can actually see that it happens at 0.4 seconds. So the maximum or the amplitude is reached at 0.4 seconds. Let's go to the left-hand side. E, we're asked at what point we reach the maximum acceleration. And acceleration is the derivative of velocity. And the maximum velocity for a cosine is that when it reaches 0 here and here. And because over here there is no acceleration, and here it's a maximum acceleration. That's when this can also be solved by looking at this equation with a sine function. It's the same points when the sine reaches a maximum. So here and also here. Okay, and that will be given at 0.4 and 1.2 seconds. So it's actually 0.4 seconds plus an n, just a constant or a number, times the period. That's when we will reach those times. So it's 0.4, sorry, and half should be, because we reach the maximum acceleration at 2 points here and here. But this is not relevant right now, so we reach 0.4 and 0.8 seconds. So we also have to find what the maximum acceleration is, and we saw from before that x squared is equal to minus a omega squared times the sine omega x. And the maximum is, of course, when sine is 1 or minus 1. And that means that the amplitude of the acceleration is a omega squared. And that's equal to, let's see, it's equal to 78.77 centimeter per second squared. Okay. And the last question that we're asked is what the mass is of this object M. And we can actually find it because we know from the beginning that the angular frequency omega was connected to the spring constant K and M like this, square root. And we were given that K equals 75 newtons per meters. Okay, and if we now square both hand sides, like squared, squared, and then we move the m to the left-hand side and omega squared to the right-hand side, we'll simply get that m equals to k over omega squared. That is 75 over omega is 3.93, 393 squared, and that's equal to 4.85 kilograms. So these were all our solution 5. And most importantly, when you work with oscillators, is to start off with the Newton's equations and solve the equation of motion for your movement, and then everything becomes straightforward.